Welcome to the Hidden Layer, where we decode the tech that's shaping our future. Today, we're diving into something really special, a groundbreaking paper that might just fix one of AI's biggest memory problems. Seriously, if you've ever built an AI agent that just gets lost in long documents, you're going to want to see this.
So let's just get right into it. We've all seen these crazy headlines, right? Models with a million, even 10 million token context windows. You think they could remember anything. So why is it that when you actually try to get them to reason over a huge document, they still can't find that needle in the haystack? What is going on?
Well, this core issue actually has a name: context rot. It's simple, really. The more information you cram into an LLM, the worse it gets at actually using that information. It just gets overwhelmed, details in the middle get completely forgotten, and the performance just tanks. But what if we've been thinking about this problem all wrong? This paper shows us a totally new way forward.
And you are definitely going to want to stick around for this one, because toward the end, we're going to reveal a completely counterintuitive finding from this research, something that shows how giving your AI agent a supposedly better tool can actually make it fail miserably. It's a critical lesson for anyone building these systems.
Okay, so let's really set the stage here. We need our AI systems to reason over massive amounts of text. We're talking scientific archives, entire legal libraries, huge code bases. And let's be honest, the current approaches just aren't cutting it.
The two go-to solutions both have some pretty serious flaws. Just making the context window bigger? Well, that leads straight back to that context rot we just talked about. And standard RAG, retrieving relevant chunks of text, it's often just too rigid. It can't handle those complex, multi-step questions where you need to find one clue just to figure out where to even look for the next one. And this brings us to the core idea of this research, this huge shift in thinking. What if, instead of treating the LLM like some mystical oracle that we just stuff information into, what if we treated it like a software developer? So this is the aha moment. The old way was all about pushing these massive blobs of text into the model's uninterpretable brain, just hoping it figures it out. It's a total black box. The new way completely externalizes this process. We give the model a workspace, like a file system, and let it use tools to actively search, filter, and process the information, exactly like a programmer would. All right, so what does this coding agent actually look like in practice? Let's break it down. Okay, look at this, because it shows the shift perfectly. On the left, you've got the old way, all that context just jammed together. But on the right, that same text is organized into a file system that the agent can actually navigate. It doesn't read it all at once. Instead, it interacts with it using a terminal and a Python interpreter. It can literally write shell commands and code to explore the data itself. And the key word here is autonomy. We are not giving it a rigid pipeline and telling it how to solve the problem. The agent gets to decide the best strategy on its own. Maybe it's a simple keyword search, or maybe it needs to write a whole custom Python script to parse the data. That flexibility is exactly what makes it so powerful. And this is just a brilliant illustration of the process. So the agent's task is to find the last spell cast in every episode of a super long D&D transcript. Its first try fails because it doesn't know all the spells. But it doesn't just give up. It actually inspects the failure, discovers new patterns, like the phrase uses lay on hands, and then refines its own code. It is literally debugging its own logic. This isn't programmed in. It just emerges naturally because it's trained to be a coder. Now, this all sounds really cool in theory, but does it actually work? Well, yeah, the results are nothing short of astonishing. On one of the absolute hardest long context reasoning benchmarks out there, this new approach didn't just get a little bit better, it saw a 56% relative improvement over the previous state of the art. I mean, that is a massive leap forward. And that wasn't a fluke. Across 5 different long context benchmarks, and we're talking a huge range here, from hundreds of thousands of tokens all the way up to a mind-boggling 3 trillion tokens, the coding agent set a new state-of-the-art on 4 of them. It just consistently blows past everything from standard RAG to models with massive context windows. All right, so for all you engineers watching, this is probably the most important part. How can you actually use these ideas and build this yourself? It's actually surprisingly straightforward. So the real power here comes from the agent's ability to adapt its strategy to whatever task you give it. It is not a one-size-fits-all tool.
the paper found two main strategies that these agents just kind of develop on their own.
So first up, for those really complex questions where you have to connect multiple pieces of information, agents use something called iterative query refinement. Just look at this trace. To find the pro gamer, the agent has to connect the developer to their founder, to their spouse, and so on. It does a series of simple searches, using what it finds in one step to build the query for the next. It's chaining clues together, which is something standard RAG is just terrible at.
But then, for analytical tasks like counting things or finding patterns, the agent completely switches gears. It realizes searching just isn't efficient. So instead, it writes its own Python script to do what the paper calls programmatic aggregation. In this example, it literally writes code with regex patterns to parse the text, count up all the contradiction labels, and find the user who has the most. And here's the best part. Not only is this way more accurate, but the code it generates is verifiable. You can actually read it and check its logic.
So the big takeaway for you is that you can start doing this today. First, stop thinking of your data as a single giant document. Structure it as a file system, folders and text files. Second, just grab an off-the-shelf coding agent, like one of the GPT-4 models. Third, give it a simple environment with a terminal and a code interpreter. And finally, and this is the most important step, just give it the problem and get out of the way. Let it work. Don't over-constrain it.
Okay, remember that surprise I promised you at the beginning? Well, here it is. The researchers thought, hey, what if we give the coding agent a standard retrieval tool, like the kind in RAG systems? That should make it even better. But the results were shocking. It often made the agent's performance worse.
They actually gave this a name, the retriever trap. Turns out, when you give the agent a shiny new retrieval tool, it gets lazy. It becomes totally reliant on it and stops doing its own deep digging with simple commands like grep or writing its own scripts. And since no retrieval tool is perfect, this reliance causes the agent to miss crucial information it would have found on its own.
And this all boils down to one powerful takeaway. We need to stop treating our LLMs like these magical oracles and start treating them like junior developers. Give them a clear workspace, a good set of tools, a well-defined problem, and then the autonomy to go solve it. The results really do speak for themselves. And that leaves us with a really fascinating final thought to chew on. This research seems to suggest that the lines between processing natural language and processing code are getting blurrier and blurrier. So if structuring our text like a code base is the secret to unlocking true long-context reasoning, what does that mean for the future of AI development? What does it mean for how we interact with information itself? It's a pretty profound question to consider.